about the specific details that you want from that sample space. Right? We had an example last week with a jar of balls. I love those jar of balls. Okay? And we had a sample space of, I think, what was it, 10 or 11 balls in there. Okay? That's the size of your sample space. And then we want to find the probability of drawing, like, a green ball. Okay, so your total sample space was 11, and there were only 5 green balls in your sample space. The probability would be 5 out of 11. Okay? Know your sample space, and then you talk about the specifics. Okay. Then, if you look at example 18 in your lecture notes, on the slides, when we give you this pretty picture to visualize what's going on with the set, we have the giant rectangle. The rectangle represents your sample space. That's everything. Then, within your sample space, that circle represents those specific details that you're looking for, right? Events that have a particular characteristic. We call the complement of those specifics everything else in the sample space that you're not looking for. Okay? So, say we've got all of the students in Math 101. That's our sample space, right? And in this room is the set of students in sections 1 through 6. The complement of this set would be all of the other students in Math 101, right? Make sense? We have the entire sample space, all Math 101 students. We have the specific set of this class. If I want the complement of this class, I don't want this class, I want the complement. And that's everybody else that's not in this class, but is still in Math 101. Make sense? Okay? Oh, it's 5. 8 a.m. We're still waking up. Some of us. Okay. Let's go to example 20. When a single card is drawn from a standard 52-card deck, what is the probability that it will not be an ace? Okay, well, let's start with our sample space. Sample space is best?
52.
52 cards, right? One deck of cards. 52 cards. Cool. Okay? Well, how many aces are in a deck? 4 aces in a deck. Okay? This is where that whole idea of a complement comes in. Okay. So 52 cards. 4 aces within those 52. Okay, so if there's 4 aces, how many cards are not aces? 48. All the other ones, right? So, go back to the question. What is the probability that it will not be an ace? 48 out of 52. If you reduce that, both numbers are divisible by 4, you get 12 out of 13. Yes? Okay. So this is where that whole idea of complement comes in. Well, we know the aces. We know how many aces there are. You use that information to complement. Is that a question?
What did you get full time?
How many aces are in the deck? That's right. This is a regular deck of cards. 0.23, gives us a grand total of 0.64. Okay. So this is the probability of students being in the top 40. Without using the chart, how could you find, or sorry, you do have to use the chart for this one. How do you find the probability that the student is not in the top 20% without adding things together? Instead of adding, you can subtract. Okay, here's the fun fact to remember about probability distributions. They always add up to 1 or 100%. 1 and 100% mean the same thing. We're talking about probability. So, if you know the whole thing adds up to 1, and you want the ones that are not in the top 20%, you would do 1 minus the probability of being in the top 20%. Right? We're cutting away the chunk that we don't need. We don't need the piece that's in the top 20%. So 1 minus, let's see, 0.41 is equal to, let's see, is that 5.9 or 0.59? Yeah. Yes, no, maybe so? Okay. Are we getting this idea of complement? Kind of sticking? Okay. Now, events involving or, because sometimes you don't have just one thing happening at once. Sometimes you got more than one thing occurring. That's when we start seeing cases where you use the word or and. So let's start with what happens if you see this or this happening. Okay? When you see the word or, probability, you've got addition. Okay? And another fun fact, we call two events mutually exclusive if they have no outcomes in common. So one example would be rolling a die, tossing a coin. Rolling the die has nothing to do with the result of tossing the coin. They are two completely different things, so those are two mutually exclusive events. Okay. Another property, if two events are mutually exclusive, like I just said, they have nothing in common, we write that in symbols using this. We say that their intersection is the empty set. That's what that stands for. So if the intersection is the empty set, it means these events have nothing in common. This is a very specific thing. You have to look for those keywords. Mutually exclusive. Only when two events are mutually exclusive do you know that is true. Let's apply our addition rule. Say we have two events, A and B, and they could have something in common. So these guys are not necessarily mutually exclusive. You're not sure. So if they could have something in common, we have the following formula. That should be, let's see, P plus A, or sorry, P of A plus P of B minus P of A and B. Okay, so the probability of the first thing happening plus the probability of the second thing happening, minus the probability that they both happen. Okay, minus the probability of the stuff they have in common. Mathematically, here's the formula, here's what that looks like. The probability that A or B happens, the formula is find the probability of A plus the probability of B minus the probability of their intersection. So yeah, minus the probability of what they have in common. Right? Let's apply this. There's our sample space. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Subset, or a specific group from our sample space, A, is all of the odd numbers from the sample space. B is the set of all numbers greater than 5. It's another specific chunk of our sample space. And C is the set of all even numbers. Yet another specific piece from our sample space. Okay? If a number is selected at random, okay, blindly choosing a number, find the probability that you choose something from A or something from B. Okay, well, let's write out the formula to start. The probability of A or B happening would be the probability that you choose something from set A plus the probability that you choose something from set B. But then you have to subtract from it the probability that you choose something that's already in common. So minus the intersection. Okay, minus the probability of something that is in both A and B. All right, here we go. Well, in terms of odd numbers from our sample space, how many odd numbers are there? 5 odd numbers. And how big is your total sample space? 10. So the probability of choosing something that's an odd number, so something from set A, is 5 out of 10. All right. How about something from set B? How many numbers are greater than 5? 5. There are 5 numbers greater than 5, and our total sample space is size 10. Okay. So that's probability that you choose an odd number. That's probability that you choose a number greater than 5. But now we need to see, are there any odd numbers that are also greater than 5? Sure. How many? Greater than 5? 2, 7, and 9. Odd numbers, my darling. 7 and 9. Minus the 2 odd numbers that are also greater than 5. So minus 2 out of 10. Put these together. You get 10 out of 10 minus the 2 out of 10, right? I'm adding the 2 fractions together first. That becomes 8 out of 10 and reduces to be a probability of 4 out of 5. You can also use a handy-dandy calculator to give you the same answer. Make sure you put your fractions in parentheses. So, parentheses, 5 divided by 10, close parentheses, plus. Parentheses, 5 divided by 10, close parentheses, minus parentheses, 2 divided by 10, close parentheses. Always put your fractions in parentheses when you come to a calculator. Okay? Part B. Find the probability that you choose something from set A or something from set C. So, find the probability that you choose an odd number or even number. Well, let's follow the formula first. That's going to be the probability of A plus the probability of choosing something from set C. And then again, you have to subtract from it anything that they have in common. Minus the probability of A intersects C. Okay. Well, what's the probability of choosing an odd number? 5 out of 10, right? There's 5 odd numbers out of your total sample space of 10. What's the probability of choosing an even number? 5 out of 10. Okay. What's the probability of choosing a number that is both even and odd? That's 0. No number is both even and odd. It's either even or it's odd. It can't be both. Okay? So, fun fact. Sets A and C, since their intersection is 0, what do you know about A and C? They are mutually exclusive. See how the intersection have nothing in common? Probability of A intersects C is equal to 0. When the intersection is equal to 0, the two sets are mutually exclusive. Okay? Keep that in mind. Let's keep simplifying. Well, 5 out of 10 plus 5 out of 10 is just 10 out of 10, which gives us 100%. Or just 1. Okay. You have a 100% probability that you're going to choose either an even number or an odd number. Well, yeah, of course, because those are the only 2 numbers that are in the set. How are you doing so far? Probability. More probability with that damn word or.
13.
13.
There's 13. 2, 3, 4, 5, 6, 7, 8, 9, 10. Jack, queen, king, ace. Right? Okay. You gotta go all the way through that. Oh, wait, sorry. I'm looking at the wrong thing. How many kings are there? 4. My bad. Sorry, you're correct. There are 4 kings in the entire deck out of 52. Okay. That reduces to be, we'll leave this 452 for now. All right. Here's what I was talking about. What's the probability of drawing a diamond?
13.
There you go. There are going to be 13 diamonds in the deck. Right? That's the whole suit. There we go. That's where I was at. So 13 out of 52. All right. Now the last piece we need is the probability that it is both a king and a diamond. How many kings and diamonds are there? 1. In the whole suit of diamonds, there's only 1 king. So 1 out of 52. Okay, there's the 3 pieces we need, so let's plug into our formula. Travis said king or dice. He says king or dice. Right, king or dice. The formula says you take the probability that it's a king plus the probability that it's a diamond, and you have to subtract away the part that's in common. So what would be in common is king and diamond. It's all part of the formula. If you look at the wording, I think it's like 2 or 3 slides back. So, we take the probability that it's a king plus the probability that it's a diamond. And then we subtract the probability that it's a king and a diamond. You have to subtract this piece of common because if you don't, you're actually counting something twice. So you don't want to repeat count something. That's why you have to cut away the part that's common. So this becomes 4 out of 52 plus 13 out of 52 minus 1 out of 52. So 4 plus 13 gives us 17. 17 minus 1 gives us 16 out of 52. If you reduce that with your calculator, you get 4 out of 13. So again, you take the probability of the first occurrence plus the probability of the second occurrence. You have to subtract away the part that's in common. Otherwise, you're double counting. Another one. This time with a single die. What is the probability of rolling a 2 or an odd number? Okay. Let's write our formula now. Probability that it's a 2 plus the probability that you're rolling an odd number minus the probability that it's a 2 and an odd number. I know it looks kind of funny, but like I said, we're sticking with the formula on this one. Okay. 1 die, so what's the probability of rolling a 2? 1 out of 6. There's only 1 2 on the 6-sided die, so 1 out of 6. Plus, okay, what's the probability of rolling an odd number? How many odd numbers are there? 3. All right. What's the probability of rolling a 2 that is odd? 0. It's just an even number, so that can't happen. So these 2 events are what we would call mutually exclusive. They have nothing in common with each other. 2 is not an odd number. Right? Put it together, we get a probability of 4 out of 6, which will reduce to be 2 out of 3. All right. That is how you do probability when you see the word or in a problem. Doing this or this. Sometimes, even though you have 2 things happening, 2 or more things second thing I want to know, the second event, what's the probability that I run out of gas? So something happened first, and then I want to know what's going to happen later. What's the probability of that happening? Let's take a look. The probability of an event must be computed using the knowledge that something else has happened already, or is happening, or will happening. Timing does not matter in this case. This is what we call conditional probability. So, we are finding the probability of an event happening with the condition that something else happened, or is happening, or will happen. Right? So it's still two things going on. It's just how they are happening at the same time is different here. Okay. The probability of our event B, computed on the assumption that another event has already happened, is the conditional probability of B given event A already happened. Mathematically, you write it like so, and you read that. B given, so vertical line, given A has happened. Okay? Here's the formula. So, the probability of B given A is equal to the probability that A and B happen divided by the probability that A happens. Okay? So you take the probability of the intersection over the probability of the first event. Okay, B is the second event. Seems a little mathy, a little wordy. Let's see if we can apply it. We have a sample space, 2, 3, 4, 5, 6, 7, 8, 9. Single number is chosen at random, and we have two events. Part A, selected number is odd, and part B, the selected number is a multiple of 3. All right, so this kind of builds up towards the last bit. What's the probability of drawing something with a multiple of 3 from that sample set? Yep, there are 3 numbers that are multiples of 3, 3, 6, and 9. Paired on sides of that sample space. How many numbers are there?
8.
There's 8, not 9. 3 out of 8. It's not reduced. Okay. Now, the next thing. What's the probability that you draw something from A and B? All right. So I'm going to go up yonder. That would be how more to write. So the probability of A and B would be the probability of A intersect B. Okay. So I want the probability that the number is odd and is a multiple of 3. Odd and multiple of 3. I'm writing everything out. And I heard someone say it. 2 out of 8, which reduces to be 1. Okay? Is that clear? Part B. Alright. Part C. For some reason it renumbered it. That's supposed to be C and D down there. My lecture notes have C and D. Part C. What is the probability that we draw a multiple of 3 provided the first number you draw, or given that the number is odd? Okay. Follow the formula. So, we want probability that a number is a multiple of 3 and odd. Divided by the probability that the number is odd. Okay? Well, the probability that it's a multiple of 3 and odd we just did in, what was that, part B. So the top of this is going to be 1 out of 4. And the probability that the number is odd is 4 out of 8. into your calculator, you should get 1 out of 2. So remember, put those fractions in parentheses. So parentheses, 1 divided by 4, close parentheses, divided by, parentheses, 4 divided by 8, close parentheses. You should get 1 out of 2. Okay. Does everybody have this written down? Because I need to erase, so I have room to fill in the last part. Anybody still writing for part C? Okay. All right. Part D. Probability of A given B. So I want the probability of choosing an odd number given that the number is a multiple of 3. So we're asking it in a different order. It will change the outcome. It will. Okay. So you start with, well, if you do probability of A given B, that means you start with the probability the number is odd and a multiple of 3 divided by the probability that it is a multiple of 3. Because of the order that the question has been asked, that's why you're dividing by something different. Okay. All right. What's the probability that a number is odd and a multiple of 3? 1 out of 4. We found that. All over. What's the probability that the number is a multiple of 3? That it's a multiple of 3. That goes to part A. Find the probability that select number is a multiple of 3. So 1 out of 4 divided by 3 out of 8. Plug that into your handy dandy calculator. You should get 2 out of 3. It does, in fact, the final answer. Pay attention to the order in which the question is being asked. All right. Moving on. Okay. More with conditional probability. We have a given chart, and along the far right column, those are your totals for all of the hardcovers, all of the paperbacks, and then the bottom right corner is all of the books total. All right. If Jackie chooses one of these books at random, find the probability that it will be a hardcover. Okay? Well, how many hardcovers are there total? 8. And there were how many books total? So 8 out of 20 will reduce to be 2 out of 5. So 2 out of 5 books will be a hardcover. Now, for part B, what's the probability that she will draw a book that is fiction given that it is a hardcover? Let's write this mathematically first. So we want the probability that she gets a fiction given hardcover. Okay. So if you write out the formula, that's the probability across the top that it is both fiction and hardcover. So you take the intersection across the top. And then you divide by the probability that it's a hardcover. Follow the formula. Looking at our chart, what's the probability of choosing a book that is both fiction and hardcover? 3 out of 20, right? And what's the probability of drawing a hardcover? In general, any hardcover. What was it? 8 out of 20. Okay, so if you reduce that on your calculator, you should get 3 out of 8. That is the probability that she chooses a book that is fiction, given that it is also a hardcover. given because bonus part C, if I want a book that is both hardcover and fiction, look at your chart. Hardcover, fiction. There are only 3 books that are both hardcovers and fiction. So that's the difference there. So 3 out of 20. Oh, Siri. Siri, can you help us? Tell us what probability? Siri, search for conditional probability. We need help. Part D. Okay, again, pay attention to the wording. What's the probability of choosing a hardcover given that it is a fiction book? Okay, let's write it out mathematically. So the probability of H given F. Okay, so we're doing it in the reverse order that we did in part B. Let's write it out. So probability of H intersect F, so hardcover and fiction, divided by the probability that it is strictly fiction. Well, the probability that it is both hardcover and fiction, we found out is just going to be, look at your notes, 3 out of 20. Divided by, well, what's the probability that it's a fiction book? 11. Look at the column for fiction. How many fiction books are there total? 11. So the probability that it's just a fiction book, I don't care if it's hardcover, paperback, just fiction. 11 out of 20. Good. Simplify that on your handy-dandy calculator. You should get 3 out of 11. This sounds so surprised. It's not a big thing. All right. From here, if you look at your notes, you are able to complete homework 7, but hang with me because we're going to jump into a little bit of homework 8. Bless you. You're welcome. Okay. Possible exam questions. Make notes to yourself. Okay. So this is all the possible combinations you can get when you roll a die, or a pair of dice. Pair of dice. This is already in your notes. Like this, a chart like this is already there. So all you need to copy is the question. Your TAs will also get this set of slides for your lab this week. Okay, so you can ask them about it then. If A is the event of rolling an 8 and B is the event of the red die being a 5, what is the probability of A or B? So what is the probability of rolling an 8 or the red die being 5? So the picture is just all of the possible pairs that you can roll. The values on the left are all the dice on the left are red, all the dice on the right are green. If you're making notes to yourself, I know you got them. Okay, so again, you can ask your TAs for a copy of this slide if need be. There we go. Okay. 4 jars of balls. Oh my goodness. Okay. Jeff is drawing 2 balls from the jar without replacement. Okay, well, let's consider something for a second. We're still talking about probability, so we still have to figure out our sample space. The key words here are without replacement. Okay, say I have 100 students in this group. Okay, and so that means the sample space would just be 100. And I choose a student for a volunteer, right? Well, how many people do I have left to choose from for my second volunteer? 99. So, without putting that student back, I have changed the sample space for the next choice. Make sense? Right? Right? Because I'm not putting them back. I'm not throwing them back into the jar. Okay. So, if Jeff draws 2 balls from the jar without replacement, not putting them back, given he draws a red ball first, find the probability that he draws a blue ball second. Okay, so, again, we're talking about without replacement, he's not putting the red ball back in. First things first, we need to know the probability that he even drew a red ball. Alright. That part is just regular probability like we know how to do. So the probability that he drew a red ball would be what? 5 out of 8. But he didn't put it back. So we'll call that P1, because that was his first choice. On his second choice, P2. Well, what's the probability that he drew a blue ball? There's still 3 blue balls in there, but our sample space is not 8 anymore, it's 7. 3 out of 7. Okay, find the probability that he draws a blue ball second. 3 out of 7. That's how that works. Don't worry, we got more. Now, the multiplication rule for probability. If A and B are any 2 events, then, okay, so in the last set of slides we talked about the probability that A or B happens. Now we're talking about the probability that A and B happen. Okay? First time it was, oh, well, this can happen or this can happen, I don't really care which one. But now we want both things for sure to happen. That's the difference here. Okay? So the probability that A and B happen is given by the probability that A happens, and then the probability that B happens, given A happened first. It seems so wordy, but think about it. Go back to this example right here. Find the probability that he drew a blue ball, provided he drew a red ball first. That's all we're talking about. Here we go. Now, the other thing we need to consider. Independent events happen in terms of one of them has no effect on the probability of the other. Perfect example. Coin toss. Say you toss a coin 3 times. Will your first toss affect what you get on the second toss? Nope. Will it affect what you get on the third one? They are all independent events. Okay. If it does not have any effect on what happens next, it's independent. It has nothing to do with the other one. Okay. If 2 events are independent, then the probability of both things happening is just the probability of the first times the probability of the second, instead of that weirdness that we saw on the previous slide. We like independent events. Calculating the probability is a lot easier. Okay. Here's an example. Flipping a coin and rolling a die. Right? Flipping a coin has no effect on what's going to happen when you roll the die. They are independent. Okay. What is the probability that you get a heads and roll a die? Okay. So the probability that you roll heads is what?
4 times.
one together, the probability is 1 out of 12. Yep, 2 times 6. Alright. More balls and jars. Here we go. Alright. 2 parts to it. Find the probability that Jeff drops a red ball and then a blue ball in that order. Okay? So, we would take the probability that he draws a red ball. Just R. And then we multiply it times the probability that he draws a blue ball. I'm color coding just for you. What's the probability that he draws a red ball?